Hello class, this chapter will cover electric potential energy, electric potential, and electric potential difference. 3 terms you should remember. First, let's start with the definition of electric potential energy. A great analogy is gravity potential energy. You can think of electric field lines as gravitational field lines, which points towards the center of the earth, and the positive charge particle as a rock. If you hold up a rock in the air, it has high gravitational potential energy relative to the ground. If you drop the rock, it will lose potential energy but gain kinetic. This works the same for a charged particle. If you place a positive charged particle at high electric potential energy point in the electric field, it will move along electric field lines and gain kinetic energy while losing potential energy. Okay, so now we just defined electric potential energy on a charged particle. Now the definition of potential is without the charged object present. The electric field arrows point away from high potential towards the negative potential. So high potential is along the positive side of the plate, and low potential is all along the negative side of the plate. The variable used to define electric potential is V. Now, if we have a negative charged particle present instead of a positive particle, the potential stays the same, but the potential energy of the negative charged particle is high at the opposite end now, and the low potential energy at the other end. Please note that potential energy and potential that we just covered are 2 different definitions. The formal definition of electric potential is electric potential energy per unit charge, which is shown in the equation. Electric potential, capital V, equals potential energy over charge. And don't get confused, but the unit for potential is also capital V, which stands for volts. Okay, now for the third definition, you should know that what is electric potential difference, which is, as the definition sounds, the potential difference between 2 points, say point A and B. In the figure, point A is at the positive plate and point B is at the negative plate. Now, since taking the difference between 2 numbers is relative, it's conventional to set the lowest potential to 0. In the figure, that would be at point B, or the negative plate would be set to 0 potential. Another way to think about potential difference is this equation. It's the change in potential between 2 points. In your textbook, though, it uses the top equation with letters A and B. Now, a definition you should definitely remember is that potential difference is the definition of voltage. You must have a difference in potential to have a voltage. Voltage and potential difference are terms that we'll use interchangeably quite frequently. Therefore, if the definition of potential is potential energy over charge, then potential difference, or voltage, is just the change in potential energy over charge. Here's an analogy for potential energy that I mentioned earlier. The more massive the charged particle, the larger the potential energy. Just like with gravitational potential energy, the more massive the rock, the larger the potential energy will be. Alright, I think we're ready for our first example. Suppose an electron is accelerated from rest through a potential difference of 5,000 volts. What is the change in electric potential energy of the electron? The equation used is potential difference equal change in potential energy over charge. Then rearrange the equation to solve for change in potential energy. From there, it's just a plug and chug. Notice that the charge for an electron is 1.6 times 10 to the negative 19 coulombs. I would write down this number for future reference. Also remember that electron has a negative charge. Multiply that by 5,000 volts to get negative 8 times 10 to the negative 16 joules. The last thing is don't forget that the unit for energy is in joules. For part B, we want to find the kinetic energy. Well, if we know the change in potential energy, we can use conservation of energy to find the change in kinetic energy. And according to conservation of energy, change in kinetic energy equals the negative change in potential energy. So the change in kinetic energy, or final kinetic energy, since it starts from rest, is positive 8 times 10 to the negative 16 joules. Okay, so the last question is finding the final speed of the electron. Well, if you know the change in kinetic energy, finding the final speed can be easily found by using the definition of kinetic energy, which is 1/2 mv squared final minus 1/2 mv squared initial. And we know the electron starts from rest, so this goes away. And from there, we can solve for the final velocity, which equals the square root times 2 times 8 times 10 to the negative 16 joules all over mass. For m, we plug in the mass of an electron, another value to write down as future reference. And we get the final speed of the electron to be 4.2 times 10 to the 7 meters per second. So basically, the electron is moving 42 million meters every second. Here's a third equation for electric field, but this equation is used for finding the electric field strength between parallel plates, which is negative potential difference divided by the distance between the plates. Another way I like to write this equation is potential difference, or voltage, equals negative ed. Alright, let's do an example. Two parallel plates are charged to produce a potential difference of 50 volts. If the separation between the plates is 0.05 meters, calculate the magnitude of the electric field in the space between the plates. We'll apply our new electric field equation, which equals negative potential difference over distance. And that's pretty much it, except for plug and chug to get 1000 volts per meter. Two things to notice. One is that I didn't include the negative sign because we're only looking for the magnitude. And second thing to notice is that there's another unit for electric field, which is volt per meter. The next definition to learn is equal potential lines, which is a line where potential is constant. So anywhere along the dotted green line in the figure, the potential is the same value. For example, if we set the lowest potential to 0, then all along the negative plate is 0 potential. Along the middle of the plate has a potential of 10 volts, and all along the potential plate, the potential is 20 volts. A good analogy to equal potential lines is elevation lines on a topographic map showing the change in elevation for mountains. But remember, along the elevation line there's no change in elevation. It's constant at the same value. Or on a weather map, there are isobars to show the change in pressure. So the equal potential lines you see show the change in potential, and like elevation lines, the potential does not change along the equal potential line. And if there's no change in potential, there's no voltage. In the figure, we can see that there's a potential difference, or a voltage, of 20 volts across the plates, because, well, 20 minus 0 is 20 volts. Last note, notice how the equal potential lines are perpendicular to the electric field lines. If you have 2 point charges of opposite signs, the equal potential lines look like this. Another unit you should be familiar with is electron volt. An electron volt is another unit for energy, because if we use joules all the time at the atomic level, it would be a small number. So for every 1.6 times 10 to the negative 19 joules, you have 1 electric volt. 1 electron volt is the energy gained by an electron moving through a potential difference of 1 volt, as seen in the equation below.